Good morning, everybody. Welcome to this session. In this session, we will look into the parallel circuits. And when we are so far, we did the analysis of the RLC, then series combination of RL, RC, and series combination of RLC. Now, when we are working with the parallel circuits, you have to remember that the concepts are very similar. Now, we studied about the parallel circuits in DC circuit. So similar kind of analysis we can do. So now you understand what is the impedance. Whenever you have a load, that is a AC load, you have to take it as a impedance. So there are a couple of ways we can work on these parallel methods. We will see them, and we will try to solve one or two problems based on that. In the exam, you may not expect too many like parallel combinations. Maybe like two parallel combination that you can expect. Means suppose an RL component is connected in parallel with the RC component, and that parallel combination is connected to an voltage supply. That kind of a problems you can expect. To solve parallel AC circuits, there are a couple of methods that are available. One is the phasor diagram, drawing the phasor diagram. You are already aware, we looked into how we can draw the phasor diagram for the voltage, applied voltage, and the resulting current. In case of a pure resistance, voltage and the current are in phase. In case of a pure inductance, current lags the voltage by 90 degree. In case of a pure capacitance, current leads the voltage by 90 degree. If it is a RL circuit, then current will lag the voltage by an angle phi. And if it is a RC circuit, current will lead the voltage by an angle phi. That angle phi can be calculated. And if it is a RLC circuit, depending upon whether XL is more, XC or more, we can get the phasor diagram. So with that understanding, we can draw the phasors, and using those phasors, we can solve. Then next one is the phasor algebra method, then equivalent impedance method. Okay, so we will see equivalent impedance is also one easy way to solve the parallel circuit. And then admittance method, we will not look into the admittance method. So in exam, they don't expect you to use any particular method. Any method is fine. So there is no specific method is required. Let us start with the phasor diagram. So for this, we are considering two impedances that are connected in parallel as shown in figure here. So this is the circuit diagram. We have a RC circuit and we have a RL circuit. Uh, this R1 and C1, they are connected in series, and we have R2 and L2 connected in series, and this combination is connected in parallel. So you can see it is connected in parallel across a voltage source of voltage V, capital V, that is RMS value, which will result in the current I, capital I, that is the resulting current, RMS value of the total circuit current. And we know the same principle. Whenever current comes to a branch, if there are multiple paths, the current will get divided into those paths. Then when current comes to this node, current will flow in, some part of the current will flow here and some part of the current will flow here. This is I1, current I2. And in case of a I1, so this path is what you can replace this complete path by one impedance, that is Z1. And what would be the value of the Z1? First we will going to calculate the XC, right? XC1 or XC, whatever you want to call. XC1 is equal to 1 upon omega C1 is equal to 1 upon 2 pi FC1. So you know the XC1 and R1. Then what would be the Z1 here? Z1 is equal to square root of R1 square plus XC1 square. And in case of a parallel combination, if you remember the parallel circuit characteristics, so this combination is in parallel with this combination, and across which we have applied a voltage. Now, when we applied a voltage V, the applied voltage V across this combination is exactly same as this combination. So what is the voltage across this R1 C1 combination? This is applied voltage V. or what is the voltage across this combination? That is also V. Now we know the voltage across this combination is V and the current flowing is I1. Now we know the relation between the voltage and the current. So in case of a RC circuit, what current I1 will lead the voltage V by an angle phi. By angle phi. So you can see here, this is the voltage, which is the x-axis, and you can see we can draw the current I1, which will lead by an angle phi 1. And how to calculate phi 1? We can use any method. Okay, so tan phi we can calculate, or cos phi, and based on that we can find the value of the phi. Then this is the one branch current I1. Now you know how to draw the I1. Then similarly, this branch I2 current is the I2, applied voltage is capital V. The same voltage is applied to both the branches. In case of a RL circuit, we know that current will lag the applied voltage by an angle phi. And how to calculate that phi? Using the value of the R and the XL. So you can calculate, you can use the tan phi function or the cos phi function. So in this case, what this particular impedance is Z2 is equal to square root of R2 square plus XL2 square. And what is XL2? L2 is given. XL2 is equal to omega L2 is equal to 2 pi f L2. That's how we can calculate this value and impedance. And this current is, you can see from this phasor diagram, the current I2 is lagging the voltage by an angle phi 2. Now if we take the phasor sum of I1 and I2, that will give us the actual current, that is I, that is flowing in the circuit. And relation between the voltage and the current, we can be easily found out what is the phase difference between them, and accordingly we can write the equation. Now here, how to find this I? We can resolve this I2. So already we know that we can resolve I2 into x-axis and y-axis component. I2 on x-axis it would be I2 cos phi, and this would be I2 sin phi, I2 sin phi 2. Similarly, this one is what? On the x-axis it is I1 cos phi 1, and y-axis I1 sin phi 1. So you can see here, we can have two components calculated. This I cos phi is equal to algebraic sum of components of I1 and I2 along the x-axis. That is I1 cos phi 1 plus I2 cos phi 2. Similarly, I sin phi is equal to algebraic sum of the components of I1 and I2 on y-axis. And on y-axis, we have I1 sin phi 1, then minus I2 sin phi 2. This angle is minus. Okay, this angle is minus. And so what would be the actual current? Actual current would be I2 square is equal to I cos phi square plus I sin phi square. And if you simplify that one, you will get the actual current. And how to find the sin phi? We already know the I sin phi component. I sin phi is this one, divided by I cos phi. I cos phi is algebraic sum of all the components of I1, I2 on the x-axis. Then similarly, we can find the power factor. Power factor is what? I cos phi divided by I. That is how we can calculate. Then using phasor algebra. So phasor algebra is also one recommended way of solving. Maybe you can use the phasor algebra, or you can use the impedance method. So we'll see the impedance method in phasor algebra. How first thing is how these impedances are represented. These impedances are represented as a complex number. Okay, so what is a complex number? A complex number is a number which has a real part and the imaginary part. So if we have an impedance of if you have a circuit of R and C, this XR is the we can represent it as a real part, and XC1, that is in capacitive reactance, that would be imaginary part. So if I have to represent this as a impedance, Z1 is equal to R1 minus JXC1, and this would be Z2 is equal to R2 plus jxl2. That is how we are going to represent. So if it is a capacitance, you use the minus. Okay, Z1 is equal to R1 minus J XC1, Z2 is equal to R2 plus J XL2. If you are aware of the complex number, if it is in a rectangular form, we can convert it into a polar form. If it is in the polar form, we can convert it into a rectangular form. And in your calci, you can do a direct calculation of the complex number. So every calci, you can just check with the user manual how to operate your uh, calci in complex number mode. So complex number calculation can be directly done. For example, adding two complex number, multiplying two complex number, dividing two complex numbers, that we can do. So that is how it becomes very easy. Whenever you get a circuit, any AC element load, if it is RL, represent like this. If it is RC, represent like this. If it is just capacitance, then minus JXC. If it is just inductance, JXL. And if it is just a resistance, you take the real value, real number. Then you can apply the same formulas. For example, on the first branch here, so I will represent this as a Z1. What is the voltage across this? V. What is the current flowing is I1. So we know that V is equal to IZ. That is the general formula. In this case, V is equal to I1 into Z1. V is equal to I2 into Z2. And you can calculate I1 and I2. So I1 is equal to V by Z1, and if you know the value of R and XL, you can do this complex number calculation on your calci. What we will do is you will give the value of the voltage, okay, divided by inside the round brackets you give the real value of the resistance, then minus there is a complex number sign I is there in all your calci. Just you have to see your manuals how to operate that. Attach that so it will make it as a complex number. And complex number imaginary part number you have to give, that is the value of the xc, close the bracket, and if you say equal, it will give the division of that complex number. That is how you can find I1. Similarly, I2 is V by Z2. And same thing, I is equal to I1 plus I2, and this sum. And if you want to convert it to the polar form, this is called as a rectangular form. And in case of a rectangular form or a complex number form, in case of your calci also, there is a provision to convert from the rectangular form to polar form, or polar form to rectangular form. So what is a rectangular form for this is, it will get me the amplitude. What is the amplitude? Square root of R1 square plus XC1 square. Okay, and the angle, using the tan phi or the cos phi, you can find the angle. So that can be represented in the polar form. For example, here you can see in the same impedance what you represented as a rectangular form here, Z1 is equal to R1 minus JXC1. This is a rectangular form. In the polar form, how you can represent that? Z1 is equal to Z1 at an angle at an angle minus phi 1 degree. How to calculate Z1? Z1 is square root of R1 square plus XC1 square, and phi 1 is equal to, we are using the tan function, that is tan inverse XC1 by R1, or Z2 is equal to Z2 at an angle phi 2, where Z2 is square root of R2 square plus XL square, and phi 2 is equal to tan inverse XL2 divided by R2. So this is how you can find Z1 and Z2. Once you know the Z1 and Z2, I1 is equal to V by Z1. If suppose, let us say they give the voltage as 230 volts, they don't specify what angle. When they don't specify, you can take it as a 0. That is the 0th reference, means angle is 0 degree. V at an angle 0 degree divided by whatever the value you get it for the Z1 in the polar form. You can do this calculation. So this would be like 0, then minus of minus, it becomes 5, 5 1, then V by Z1. Similarly, you can calculate I2, then I1 plus I2, the total current. Then this is the equivalent impedance method. Equivalent impedance method, you remember from the parallel circuit, Suppose if in case of a DC circuit, if R1, R2, R3 are connected in in parallel, the effective resistance of the circuit, that is 1 upon R equivalent, is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on. So that is how I can find the equivalent resistance. Same thing can be applied here. Now you can see impedance Z1. So this could be RL, RC, R, whatever the combination, RLC. So Z1 we know. This is connected in parallel with Z2, Z3 and so on, Zn, which is connected across a voltage source of V. It will result in a total current of I and individual branch currents I1, I2, I3 and so on, In. I know that this total current is equal to the phasor sum of all these currents. Therefore, I is equal to I1 plus I2 plus I3 so on. And voltage across all these impedances are exactly V. We know that V is equal to I1 into Z1, V is equal to I2 into Z2, V is equal to I3 into Z3, so on, V is equal to I1 into Z1. So therefore, the I is V by Z total, right? Z total or equivalent. I1 is what? Here V is equal to I1 into Z1, I1 is equal to V by Z1 plus V by Z2 plus V by Z3 and so on. And if we cancel the V from both the sides, what we get? The total impedance of the circuit can be calculated. So the reciprocal of the total impedance of the circuit is equal to reciprocal sum of all the reciprocals of the individual impedances. That is 1 by Zt is equal to 1 by Z1 plus 1 by Z2 and so on plus 1 by Zn. Therefore, we can write, once we calculate the total impedance of the circuit, the total current, you can call it as a line current or whatever the total current, is equal to V by Zt. That is how we can calculate. And here they have taken one example where there are only two impedances. I told you most of the time they will give you two impedances. If that is the case, you can directly use this equation. Zt is equal to Z1 Z2 divided by Z1 plus Z2. So here you can represent Z1 as a polar form or a rectangular form, and you can do the simple calculation. If it is a complex number calculation, you can directly calculate this on your calc, and we can calculate the total current and the branch currents I1 and I2. These formulas can be used. Admittance method, let us not confuse. The first three methods are good enough to solve any kind of a problem. Let us try to solve some problems. Okay, so I have a problem here. Okay, a resistance of 20 ohm and coil inductance of 31.8 millihenry and negligible resistances are connected in parallel across 230 volt 50 hertz supply. Find the line current, power factor and power consumed by the circuit. So we have very simple circuit. I have two components which are in parallel. This is resistance, R is equal to 20 ohm, L is equal to 31.8. They are connected in parallel. Now, we know that in case of a resistance, the applied voltage. So same voltage is applied across the both the components. The voltage across R, that is resistance, V and IR would be in phase. So if I draw the voltage on the x-axis, IR current would be on the same axis. Then we have IL here. So voltage and IL relationship. IL, the line in the the current in the inductor lags the applied voltage by 90 degree. You can see IL lagging the voltage by an 90 degree. So phasor sum of IR and IL is nothing but the resulting current. Now how to find out that? Now 230 volt is applied across the resistor. Okay, we know the value of the resistance. So V is equal to IR into R. That is IR is equal to V by R, that is 230 divided by 20 ohms. We get it as 11.5 amperes. So this IR is nothing but 11.5 amperes. Now we can calculate XL because frequency is given, right? 230 volt, 50 hertz is given. XL is equal to 2 pi FL. pi FL, you substitute, you get it as 10 ohm. So this is inductive reactance XL is equal to 10 ohm. And IL, same formula we can apply. Applied voltage across this is V. V is equal to IL into XL. Therefore, IL is equal to V divided by XL, 230 divided by 10, 23 amperes, lagging by 90 degree. Now, how we can calculate I? I is equal to square root of IR square plus IL square, right? It forms a rectangle, right angle triangle. So we can calculate like this. The line current I is equal to square root of IR square plus IL square, and if you substitute, you will get it as 25.71 amperes. Now, how to find the power factor? Same, this angle you have to find, right? In order to find this angle, the adjacent upon hypotenuse, that is IR upon I. That is IR upon I, 11.5 divided by 25.71. You get it as 0.447 lagging. So once you know how to draw the phasor, with respect to that phasor, you can write all the equations. Next is power consumed. We know that it is V into I into cos phi. What is the V? Applied voltage. I, resulting current. So we need that total current. Vi and cos phi is known. You calculated 230 into 25.71 into 0.447. You get it as 2643 watts. That is the power consumed in that particular circuit. Next problem, we have a capacitance of 50 microfarad connected in parallel with a coil that has a resistance of 20 ohm and inductance of 0.05 Henry. So this is the circuit. So you have to remember, in the exam they will give a description about the circuit. From this description you should be able to create the circuit diagram. It is clearly told here, a capacitor of 50 microfarad is connected in parallel, means this 50 microfarad capacitor is connected in parallel with the coil. This is the coil that has a resistance of 20 ohm and inductance of 0.05 Henry. If this parallel combination is connected across 220 volt. So this is a 220 volt 50 hertz supply to 200 volt, sorry, yes, 200 volt 50 hertz supply. What we have to calculate the line current. Line current means total current, power factor and power consumed. Only the same thing we have to find out. The minute you have C given, L given, if you know the frequency, first calculate XC. So this XC is equal to what? Z1. This impedance is XC. XC is equal to 1 by 2 pi FC. You substitute the values, you get 63.7 ohm. So this is XC is 63.7 ohm. Then applied voltage across this is known. How much is that? 200, right? V into I1 into XC, or I1 is equal to V divided by XC. V is 200, XC is 63.7, 3.14 amperes. This current is 3.14 amperes. Similarly, we can find the impedance of the second. So impedance of this, before that you calculate XL. XL is equal to 2 pi FL, which will come as 15.7 ohm. Now I have to find the impedance of this branch. What is the impedance of that branch? Z2 is equal to square root of R square plus XL square. That is square root of 20 square plus 15.7 square. You get it as the impedance of this branch as 25.43 amperes. Once you know the impedance, you calculate I2, because the voltage across this branch is V. V is equal to I2 into Z2, or I2 is equal to V by Z2. You get it as 7.86 amperes. Now, look at the phasor diagram. Voltage, applied voltage is the x-axis, and if you see the I1 is a pure capacitor. So I1 will lead the applied voltage by 90 degree. So this is the applied voltage. This is a I1. It is leading by 90 degree. And second scenario, we have a RL. Okay. In case of a RL, the current lags the applied voltage by an angle phi. Okay. So you can see in this case it is phi 2, because I2 phi 2. So the I2 current is lagging the voltage by an angle phi 2. So we can calculate easily phi 2. Phi 2 would be what? If you consider tan phi, it would be XL2 divided by R. Okay, or R2. Phi 2 is equal to tan inverse XL2 divided by R2, 15.7 divided by 20. So what is 15.7 is XL, okay, this branch, divided by 20, that is resistance. We get the angle as 38.13. So this particular angle, you can see this I2, this angle is 38 point, whatever we have got, 38.13 degree. Now we can find the total current by getting the components on the x-axis. So I cos phi is equal to I1 cos phi 1 plus I2 cos phi 2. I1 we already know, phi 1 we know, I2 we know, and phi 2 we know. You substitute that value, 3.14 into cos of 90, okay, plus 7.86 into cos of 38. So cos of 90 is 0. This is component is 0. So I cos phi is 6.18 amperes. And similarly, you calculate I sin phi. I1 sin phi 1 minus I2 sin phi 2. Because phi 2 is minus sign of this. That is why we have negative sign there. This is minus angle. So that I sin phi, you get it as minus 1.71 amperes. Total current is what? Square root of I cos phi square plus I sin phi square. So is equal to, you get it as 6.41 amperes. And what would be the new phase angle? New phase angle would be tan inverse of I sin phi divided by I cos phi. I sin phi is minus 1.71 divided by I cos phi is 6.18. We get it as 15.47 degree. Now the resulting current is this, and this angle is 15.47. Power factor cos of this angle, that is 0.964 lagging, means what? The resulting current will be lagging the voltage by this angle, 15.47. Power consumed, P is equal to VI cos phi, that is 200 into 6.41 into cos phi. So power consumed is 1235.85. That is the power that is consumed. So if you want to solve this method, that is fine, or this is a phasor algebra method, or you can use the impedance. You can find the total impedance. How to find the total impedance? 1 by ZT is equal to 1 by Z1 plus 1 by Z2. Already you have calculated the Z2, and Z1 is 15.17. And how do you represent this Z1? Z1 is equal to the Z1 is equal to, one second. Okay, it is calculated here. Branch 1, Z1 is equal to, as a rectangular form or a complex number form, you represent Z1 is equal to minus J 63.7, and Z2 is equal to 20 plus J 15.7. That is how you represent. So what you are going to write, 1 by ZT is equal to 1 divided by minus J 63.7 plus 1 divided by 20 plus J 15.7. So you do the calculation directly in the calculator, and you can write the ZT. Once you know the ZT, what would be the I? I is equal to V by Z, right? V by ZT. So directly you can calculate, you will get the same answers. What you can do is, as a practice, use the that particular method, impedance method. Use the impedance, calculate the impedance. Using impedance, you find all these parameters. This is one more problem is there. You can just take a look into this problem. We see if there are any other problems. This particular, a 10 ohm resistor, 15.9 millihenry inductor, and 159 microfarad capacitor are connected in parallel to 200 volt. So all are connected in parallel. Calculate the supply current and power factor. So you can see here, L value is given and C value is given, frequency is given. So calculate XL and XC. So XL will come as 5 ohm, XC will come as 20 ohm. Then resistance is given. So they are connected across 200 volt. So this is IR, IL, IC. we definitely know the relation between the applied voltage and the individual currents. So applied voltage, take it on the x-axis, IR would be in phase with the voltage, then IL will lag the voltage by 90°, IC will lead the voltage by 90°. Okay, you can do the impedance method also here. So if you use the impedance method, what is the Z1? Z1 is equal to 10, Z2 is equal to plus J5, and Z3 is equal to minus J20. That is how you should take. And what would be the total impedance? 1 by ZT is equal to 1 by Z1 plus 1 by Z2 plus 1 by Z3. And find out the ZT. Once you know the ZT, then V is equal to I into ZT, or I is equal to V divided by ZT. That is how you can find the current. And whatever the angle you get for that current, that is the phase angle between the voltage and the current. That you can directly take. So otherwise you can solve like this. I is equal to, because IC and IL are on the same line, we can do a algebraic subtraction, IL minus IC. Therefore, I is equal to square root of IR square plus IL minus IC square. And these are the different currents we already calculated. IR is equal to V by R. This is the voltage is same across all. V by R will give IR, V by XL will give IL, V by XC will give IC. So IR 20 amperes, IL 40 amperes, IC is 10 amperes. So as indicative of this IL current, the circuit will behave like a RL circuit. And if you substitute those values, total current I, you get it as 36 amperes. And cos phi is what? IR divided by I. 20 divided by 36, 0.56 lag. So this angle, the resulting current I will lag the voltage by an angle phi. Next one is determine the impedance at 400 hertz of a 10 kilo ohm resistor in parallel with one capacitor, 0.03 microfarad capacitor. So this is also very similar. There is no difference in what we have seen. Only thing is frequency is here higher. It is 400 hertz. Other than that, conceptually everything same. You find XC, you will find once you have a XC value, applied voltage is determine the impedance. Okay, 400 hertz of a 10 kilo ohm resistor in parallel with 0.03 microfarad capacitor. So XC you found out. We arbitrarily assume that the voltage V is 10 volt because the voltage is not given, the insufficient data. So that is why this assumption V is equal to 10, and they have done the calculation. Okay, this is another problem which is in very similar line. So if it is a little different, then okay. So this we will look because they have used the polar or the rectangular form for the calculation. A capacitor 100 ohm reactance is connected in parallel with a coil of 70.7 ohm resistance and 70.7 ohm inductive reactance to 250 volt AC supply. Determine supply current, overall power factor. So capacitor, this XC is given. They have not given C, directly XC is given. XC is 100, is connected in parallel with the coil. So a capacitor is connected with the RL combination, and resistance is what? 70.7, and XL. This is directly XL is given. XL is 70.7. They are connected across 250. So you have to draw the circuit diagram so that you will have a better understanding. Applied voltage. Okay, if you take the polar form, 250 at an angle 0. Why at an angle 0? Because they have not specified. That means we can assume it is a 0. It will start from the 0th time, that is 0 degree. Coil impedance ZL 70.7 JXL. This is XL, right? XL 70.7, and you can convert it into polar. You can do it on the calci itself. This 100, how we got it is square root of 70.7 square plus 70.7 square. That is 100, and the tan phi or cos phi, using that you get angle as 45 degree. So this and this are exactly the same. This is a complex number format, rectangular format, and this is a polar format. Coil current IL is equal to V by ZL. You can directly do this calculation. V is 250 at an angle 0. ZL is 100 at an angle 45 degree. So therefore 250 divided by 100 is 2.5. 0 minus 45, 45 degree you get. This you can convert it into a complex number form. So you can calculate using the complex number itself. You can say in your calci 250 divided by inside the bracket you give this number 70 plus I 70.7 close the bracket, you say equal, you will get this value, and from that you can convert from that value to an polar form. So in your calci, you should look out for how to get this. There is something r at an angle theta in your calculator. Just look into that. If you see r at an angle theta, that will convert it this number into this form. Then impedance of a capacitor, I told you this should be represented as a minus, always minus j. So minus j 100, which is 100 at an angle minus 90 degree. Current in the capacitor, voltage divided by the this value, that is the XC value. We get it as 250 divided by 100, 2.5, 0 minus of 90. So that will become plus 90. J 2.5. This is the current in the capacitor. This is the current in the inductor. Now supply current I is equal to IL plus IC. So both are in the complex number form, right? You can easily add the, so 1.77 will remain as is. This minus J 1.77 plus J 2.5, we get it as plus J 0.73, and this is the total current in the complex number form, or it is represented in the polar form like this, 1.91 at an angle 22.5 degree, and this angle is nothing but this is the current, right? Voltage is having a reference of 0. So phase difference, what is the phase difference? The voltage current is having 22.5 degree minus 0 degree. So that is the phase phi. So cos of that angle is nothing but the power factor of the circuit. So you can solve in a similar line. We have one more example here. Here we have a RL and the RC combination. Okay, I'm sorry for that. We have one more problem here. Just you can look into this particular problem. You can convert this into this as Z1, this as Z2, and we can use the impedance method. So they have done the same. Z1 only you have to remember. Z1 is what? 50 plus JXL. Z1 is R1 plus JXL, and here it is Z2 is equal to R2 minus JXC2. Okay, that you can see Z2 is equal to R2 minus JXC2. Once you have Z1, Z2, it is same like before. You can use the impedance method. Okay, 1 by ZT is equal to 1 by Z1 plus 1 by Z2, and you can calculate, or you can use this particular methodology. And you can see here this particular problem, they have given the direct complex number form or the rectangular form, three impedances, 70.7 plus J 70.7. What is this? This is RXL. So it is a RL combination. One more RL combination, 120 plus J 160 plus 120 plus J 90. These three are connected in parallel. We have to determine the, don't worry about the admittance. 1 upon Z is the admittance for your information. Y is the admittance is equal to 1 by Z. You can find the supply current and the circuit power factor. Same method you have to use. Z1 is given, Z2 is given, Z3. In your calci, you can directly say 1 upon ZT is equal to 1 upon Z1 plus 1 upon Z2 plus 1 upon Z3. Give the complex number, put your calci in the complex number mode, then it will do the direct calculations. From the next class, we will start looking into the three phase. So this will complete the single phase circuit analysis, three phase. So whatever we talked about one phase, we will be using it as a three phases, and those three phases, uh, when you treat individual phase, it is the same thing. If you have understood clearly the single phase, the three phase is very, very simple, and we will look it into the next class. And all industrial connection